Every galaxy we've ever weighed has been hiding something. Spiral galaxies, dwarf galaxies, giant ellipticals. When we measure how fast their stars move, the answer never adds up. There's always more gravity than there is visible stuff to explain it. That invisible extra is what we call dark matter. And for 50 years, it's been the one ingredient every galaxy seems to require. Except a few years ago, astronomers found two that didn't. Two faint galaxies where the math actually closed, where the stars you can see are all the mass there is. They were called impossible, and now there's a third, and this one someone saw coming. A galaxy with no dark matter shouldn't exist. Finding a third one, exactly where a theory said it would be, might tell us what dark matter actually is. To understand why these galaxies are such a big deal, you have to know how astronomers weigh something they can never put on a scale. The trick is motion. The stars in a galaxy are like a swarm of bees. Those bees are around a hive, and the more mass packed into the center, the more furiously they have to move to keep from drifting away. Measure how fast they're moving, and you've measured the total mass pulling on them, including any mass that you can't see. And here's the thing, for every normal galaxy, that measure comes back too high. The stars move way too fast for the visible matter alone. Something unseen is gripping them. The person who nailed this down was an astronomer named Vera Rubin. Back in the 1970s, working at the Carnegie Institution, she measured how fast stars orbit in one spiral galaxy after another. And she kept hitting the same wall. The stars, way out at the edge, were moving just as fast as the ones near the center, when they had no business doing that unless some vast, invisible mass was holding them in. Her rotation curves became the bedrock evidence for dark matter, an invisible substance that outweighs everything we can see by roughly 5 to 1. It's thought to make up about 85% of all the matter in the universe. And dark matter isn't just filler either. In the standard picture, it's the scaffolding. Galaxies form inside dense clumps of it. The dark matter collapses first, and ordinary gas falls into the gravitational well that it creates. No halo, no galaxy. Which is exactly why a galaxy without dark matter isn't just unusual. On paper, it's a galaxy that shouldn't have been able to form at all. That's the wall astronomers hit in 2018 when Pieter van Dokkum and his team at Yale pointed their instruments at a faint, ghostly smudge of a galaxy called DF2, out in the direction of the constellation Cetus, in a field surrounding a larger galaxy named NGC 1052. When they measured how its star clusters were moving, the stars weren't whipping around. They were drifting, lazily. The velocity was so low that the visible stars alone accounted for essentially all of the mass. There was no room left for a dark matter halo. None. The result was so strange, it kicked off years of argument. Maybe the distance was wrong. Maybe the measurement was off. But then the same team found a second one, DF4, in the same exact neighborhood, telling the same impossible story. Two galaxies side by side, both apparently missing the one thing every other galaxy in the universe seems to carry. Now, two anomalies is a puzzle, but here's where it gets interesting, because a few years ago, astronomers noticed something about where these galaxies sit. DF2 and DF4 aren't floating randomly. They actually line up. In fact, they're part of a string of about 10 faint galaxies, all threaded along a nearly straight line across the sky, and moving in a pattern so orderly it looks less like a coincidence and more like the aftermath of something. And that straight line, 10 galaxies strung like beads on a wire, is what turned two weird galaxies into a prediction the scientists could actually test. Now, here's the idea that ties all of that together. What if DF2 and DF4 weren't born the normal way at all? What if instead of forming inside their own dark matter halos, they were born from wreckage? The theory is called a bullet dwarf collision. Picture two gas-rich dwarf galaxies slamming into each other, head-on at an enormous speed. Here's the key. A galaxy is really three things layered together: stars, gas, and typically a halo of dark matter. And in a head-on crash, those three behave completely differently. The stars barely notice. A galaxy is mostly empty space, so the stars just slip past one another and keep going, essentially untouched. The dark matter does the same thing. It feels nothing but gravity, so it passes right through the wreck like a ghost and sails out the other side. But the gas can't. Gas is thick, and gas is continuous, and gas is sticky. So when two clouds of it meet head-on, they don't pass through each other. They slam together. They shock, they pile up, and the sheer pressure of the collision strips that gas clean out of both galaxies and strands it in the middle, in a long streamer of debris trailing behind. And here's the thing, we've actually caught this in the act once before, on a much, much bigger stage. It's called the bullet cluster, two entire galaxy clusters that smash together, where astronomers could actually map the hot ordinary gas sitting in one place and the dark matter sitting in another. They were able to trace it by its gravity, sitting somewhere else entirely. Two kinds of matter physically pulled apart in the crash. The bullet dwarf idea takes that one step further. Out of the stranded gas that's now been divorced from its dark matter, a whole new generation of small galaxies condenses. Galaxies built from ordinary matter alone. Galaxies born without a dark side, without the dark matter. If that story is true, it makes a very specific promise. DF2 and DF4 shouldn't be the only ones. Every galaxy strung along that line, all 10 beads on the wire, should have formed from the same stripped gas. Which means every one of them should also be missing its dark matter. That's not a vague guess, that's a falsifiable prediction, and it's the kind of thing that can make or break a theory. So a Yale-led team with PhD student Michael Kame leading the charge went and tested it. They picked the galaxy on the trail that most closely resembled the original two, a faint smudge now called DF9, and they aimed one of the most sensitive instruments in the world at it, the Keck Cosmic Web Imager on Mauna Kea in Hawaii. This is delicate work. DF9 is so faint they needed nearly 11 hours of exposure spread across 2 nights just to capture enough starlight to measure how its stars were moving. And when the number came back, the stars in DF9 were drifting, just like DF2 and just like DF4. The measured velocity was around 6.5 kilometers per second. To see how strange that is, if DF9 had the dark matter halo you'd expect for a galaxy of its size, its stars should be moving several times faster, more like 24 kilometers a second. And the whole thing should weigh over 10 billion suns. Instead, the numbers point to a total mass of about 100 million instead, an amount the visible stars account for all on their own. No dark matter halo required, and what that essentially meant was the prediction had stuck its neck out and DF9 confirmed it. A third, impossible galaxy found exactly where the theory said to look. Now here's the part that flips the whole story on its head. You might think a galaxy with no matter is bad news for dark matter, a crack in the theory. But hang on, because it's nearly the opposite. Think about what a bullet dwarf collision actually requires. For gas to get stripped away and left behind while everything else sails on through, there has to be something else, an invisible component that doesn't interact, that passes through the wreck untouched and carries on into the distance. In other words, to make a galaxy without dark matter, you first need that dark matter that can then be separated out. So a galaxy with no dark matter doesn't undercut the theory at all. If anything, it's one of the cleanest fingerprints of dark matter that we've gotten to date. And this is where it lands a real blow against the main alternative. For decades, some physicists have argued we don't need dark matter at all, that gravity itself just behaves differently on galactic scales, an idea called modified gravity or MOND. But modified gravity has a problem here. If the extra pull were just gravity acting strangely, then every galaxy should show it. There's no way to build a galaxy that opts out. A galaxy where the stars drift exactly as their visible mass predicts, with no anomaly at all, is precisely the thing modified gravity struggles most to explain. Dark matter, as a real physical substance, handles it naturally. Remember that swarm of bees from the start? The idea that motion reveals hidden mass? DF9's bees are barely buzzing, and that lazy drift, paradoxically, is some of the cleanest evidence yet that the hidden mass in every other galaxy is really there. And the best part? This isn't even the end of the test. Remember, DF9 is only the third galaxy on a trail of about 10. The theory has effectively placed 7 more bets. 7 more galaxies that should also come back empty of dark matter. Every one is now a target, and with each faint smudge they measure, astronomers get to watch a prediction either hold the line or fall apart. The paper this story is based on is currently out in the Astrophysical Journal, and I'll drop a link below. If you want more stories where a prediction gets put to the test, please subscribe. It really does help the channel, and it's the best kind of science. And here's my question for you. If those 7 other galaxies all come back empty, does that settle the dark matter debate for good? Or would you still place a bet on modified gravity? Let me know down in the comments, and I'll see you next time.